We all have those moments, usually late at night, when you look up at the sheer scale of the cosmos, you see that starlight that's traveled for millions, sometimes billions of years, and you can't help but ask the biggest questions. Where did all of this come from? How did we get here?
That innate curiosity, that wondering,
Yeah.
it's precisely what drives science. And today,
Hmm.
we're taking that wonder and uh, applying the most rigorous scientific framework we have. This isn't just a discussion about Earth. This is a deep dive into the origin and evolution of the entire Earth system, a history that starts before our planet even existed.
This is a monumental mission, then. We've taken a stack of incredibly detailed source material articles covering everything from the Big Bang to plate tectonics, differentiation, and the emergence of early life, and we are synthesizing it all. The core theories, the stages, the massive timelines.
And our focus today is purely on that colossal journey of formation. We need to trace a line from a singular, unimaginably hot and dense point 13.7 billion years ago, through the creation of galaxies, the birth of our solar system 4.6 billion years ago, the violent formation of the moon, and right up to the point where Earth finally became hospitable to life. I mean, it's a 13.7 billion year story of physics, chemistry, and just pure cosmic violence.
That's the mission. We are going to provide you with the ultimate shortcut to understanding the history of everything.
Okay, let's unpack this. Our goal is to make those immense timescales tangible, tracing the history from that single point of energy to the first signs of life, and making it clear just how demanding, how specific the conditions needed for our existence truly were.
Before we dive into the current scientific consensus, the Big Bang, it's, I think, essential to look back at how profoundly challenging it was for early thinkers to even begin to conceptualize this. Before the 20th century, cosmology relied on these elegant but ultimately incomplete hypotheses.
They absolutely did. And the sources highlight two competing views that really dominated the pre-modern discussion. These weren't just academic debates. They represented fundamentally different views on whether our system formed through orderly processes or through, well, sheer catastrophe.
Let's start with the orderly process. The nebular hypothesis. This was put forward by Immanuel Kant, the philosopher, and later refined mathematically by Pierre-Simon Laplace in 1796. What was the central idea of their model?
The central idea was one of smooth evolution. They suggested that the sun and the planets all formed simultaneously from a massive rotating cloud of gas and dust, a nebula. As this nebula contracted under gravity, it spun faster, it flattened out, and rings of material slowly separated, cooled, and condensed to form the planets. It's a very neat, almost clockwork vision of system formation.
And their model worked pretty well for the general arrangement of the planets, but it hit a major roadblock almost immediately. The issue of angular momentum.
That's where the orderly model really struggled. In the nebular hypothesis, the sun, which contains 99.8% of the system's mass, should also possess the vast majority of the angular momentum. But empirically, the sun accounts for less than 1% of the system's rotational momentum. The planets, especially the massive outer ones, hold all the rest. This physical discrepancy, the sun spinning way too slowly, is why catastrophic theories started to gain traction.
And that brings us to the more dramatic proposal from the early 1900s, the wandering star concept, championed by figures like Thomas Chamberlain, Forrest Moulton, and later Sir James Jeans and Sir Harold Jeffrey.
Right. This model just threw order out the window and replaced it with violence. They proposed that a large, non-solar star, perhaps much larger than our sun, pass nearby. The intense gravitational tidal forces of this passing star stripped a filament of material. They described it as cigar-shaped, right off the solar surface. As the passing star retreated, that hot, stretched material cooled and condensed to form the planets.
It's essentially an external force being brought into account for the necessary material and that momentum transfer. It gives us a sort of cosmic drive-by scenario that, frankly, sounds a lot more exciting than a gently cooling cloud. But as robust as these early ideas were, they were eventually superseded by observations that applied not just to our solar system, but to the entire observable universe.
And that takes us into the modern era and the undisputed champion of cosmological theory, the Big Bang. It is the most robust and highly supported argument for the universe's origin, finally replacing concepts like the discredited steady-state universe. That was championed by Fred Hoyle, who famously, and maybe a bit derisively, actually coined the term Big Bang.
What's truly counterintuitive about the Big Bang is that it asks us to abandon our everyday understanding of physical reality. We're talking about everything, all of space and time beginning in a single point, a tiny ball.
We are talking about the ultimate singularity, a point with an unimaginably small volume and infinite density and temperature. This is the Planck epoch, the very first moment, before even time as we understand it truly existed. Within the first fraction of a second, we're talking 10 to the power of negative 36 seconds, the universe underwent an incredible, rapid, and violent expansion. We call it inflation.
That's where the idea of the tiny ball exploding comes from, but it's more accurate to say it was a huge expansion of space itself. It happened 13.7 billion years ago, and that expansion is still continuing to this day.
And the subsequent timeline is just so compressed. Immediately following inflation, we enter the quark epoch and the lepton epoch. The universe was still so hot and dense that matter existed only as this plasma soup of fundamental particles. It wasn't until the temperature dropped further that these particles could bind. Our sources stress that within the first 3 minutes after the Big Bang, the conditions were right for the formation of the first simple atomic nuclei, mostly hydrogen and helium.
3 minutes. The raw material for every star, every planet, every person, it was forged in less time than it takes to queue for a coffee. That is just astonishing.
It is, but if you could look at the universe then, you wouldn't see light as we know it. After that initial formation phase, the universe entered what is often called the cosmic dark age. And this lasted for hundreds of thousands of years.
What defined that dark age? What does that mean?
It means it was an opaque fog. The universe was too hot above 4,500 Kelvin for electrons to be captured by the newly formed nuclei. The resulting plasma scattered light constantly, meaning light couldn't travel freely. It was, like living permanently inside the sun. It wasn't until about 300,000 years after the Big Bang, when the temperature finally dropped below that 4,500 K threshold, that electrons could combine with nuclei to form stable, neutral atomic matter.
And that event, that cooling and the formation of stable atoms, that's the cosmic dawn. That's the point where the universe finally became transparent.
Exactly. And the light that was set free at that moment is still detectable today. It's the definitive piece of evidence for the Big Bang. The cosmic microwave background radiation, the CMB, it's the faint echo, the remnant heat of that 4,500 K transition point, and you can detect it uniformly across the entire sky.
But the theory relies on more than just the echo. It relies on the continuous evidence of expansion, largely thanks to Edwin Hubble in the 1920s.
Hubble's work was observational genius. He looked at distant galaxies and found that they were all moving away from us. And the farther away they were, the faster they moved. This is what we call Hubble's law, and it provided clear evidence that the universe is not static, it's constantly expanding. We see this movement via what's called redshift, where light waves from objects moving away from us are stretched toward the red end of the spectrum.
Okay, this is the moment where we need to nail the common misconception using that analogy from the sources, the inflating balloon.
Right, it's a useful starting point, but we need to emphasize the caution. If you mark points on an inflating balloon, those points move away from each other. That demonstrates how every point in the universe sees all other distant points moving away from it.
But the massive pitfall of the balloon analogy is that it implies the points, the galaxies are flying away through some pre-existing static space.
And that is the critical distinction a true deep dive listener needs to grasp. The galaxies themselves are held together by gravity. They are not flying apart. It is the space itself between the galaxies that is expanding. It's not movement through space, but the expansion of space. This raises a fundamental, almost philosophical question. If space is expanding, what is it expanding into?
That's the point where most people, including me, just scratch their heads.
And the current consensus is humbling. It's not expanding into anything. If you consider the universe as defined by space and time, then the expansion is intrinsic to that entity. You can't point to a boundary or an outside. And this continued accelerating expansion is actually driven by mysterious forces that we don't fully understand, primarily what we call dark energy.
That's a powerful nugget right there. The universe's expansion isn't just confirmed, it's accelerating, driven by something we can't observe directly. Dark energy and dark matter, which make up something like 95% of the universe's total mass and energy, remind us that for all the certainty of the Big Bang, we still know very little about the ultimate driver.
Right, so once the universe became transparent, roughly 300,000 years post-Big Bang, we had a universe filled primarily with neutral hydrogen and helium gas, and with a slight but absolutely crucial uneven distribution of matter and energy.
The unevenness, those tiny density differences, are the critical seeds of everything that followed. If the universe had been perfectly homogeneous, we would have just had a uniform thin gas cloud forever.
Exactly. Those initial density differences created slightly stronger gravitational forces in specific regions, acting as gravitational anchors. Over hundreds of millions of years, these forces began to draw the hydrogen and helium gas together.
And this pooling of gas and dust created these enormous clouds we call nebulae. And as these nebulae grew and contracted further under their own mass, they began the process of star formation.
We're talking about structure on the largest scale here, galaxies. Galaxies formed from the accumulation of these massive rotating nebulae. And within these growing nebulae, the localized clumps grew denser and hotter, initiating nuclear fusion in their cores, giving rise to stars.
It's an immense slow-motion process. The universe spent its first several billion years just collecting the raw material and waiting for gravity to do its organizational work. So when did this great celestial fireworks show, the first generation of stars, really kick off?
The formation of the earliest stars is generally believed to have taken place some 5 to 6 billion years ago, which means the universe was already roughly half its current age.
And crucially, those first-generation stars were made almost purely of hydrogen and helium, the only elements available from the Big Bang. That means they could never have formed planets like Earth.
And this is the critical transition point that links the cosmos to our local neighborhood. Those first massive stars, they lived fast and they died young in colossal explosions called supernovae. These explosions are the universe's chemical factories. It's only in the intense pressures of a supernova that elements heavier than iron like silicon, oxygen, carbon, and crucially, all the metals that make up rocky planets are forged, and then they're scattered back out into space.
So the very material that forms our bodies, the iron in our blood and the calcium in our bones, had to be manufactured and scattered by the death of a star that lived billions of years before our sun even existed.
We are, quite literally, made of stardust. Our solar system, therefore, had to form from a second or even third generation nebula, one that was enriched with these heavy elements, or metals as astronomers call them. This complex enriched nebula is the starting point for part 2.
Here's where it gets really interesting. We've traced the timeline from 13.7 billion years ago through the creation of elements by supernovae, and now we zoom down to our local corner of the Milky Way galaxy.
The formation of our solar system is a specific, well-defined event built on those galactic foundations. Our sources tell us that the enriched nebula from which our system formed began its final collapse into a core approximately 5.6 billion years ago. That core would become the Sun.
And the timeline tightens up significantly now. Once the sun started generating energy, the planets consolidated quickly. The sources place the formation of the 8 planets at approximately 4.6 billion years ago.
That speed is remarkable, and it followed a very clear 4-stage process outlined by the modernized nebular theory. This process explains how a diffuse cloud becomes the highly organized orbiting system we observe today.
Stage 1 is the gravitational collapse we just discussed. A huge lump of gas within the larger nebula forms a core due to gravity. This core then starts to spin faster and flatten into a disk, the solar nebula.
Stage 2 is the condensation phase within that spinning disk. As the material cools, matter around the core condenses into small, solid, rounded objects. These are the planetesimals. You can think of them as kilometer-sized asteroids or miniature comets. This is the crucial stage where the raw materials differentiate based on temperature.
Stage 3 is accretion. This is the violent growth phase. Larger bodies start to form by continuous collision and gravitational attraction. The planetesimals, under the influence of gravity, just stick together, sweeping up all the loose debris.
It truly is a runaway process. Once a body gets big enough, its gravitational pull rapidly increases, hoovering up more and more material. Stage 4 is the final consolidation. In this phase, after billions of smaller planetesimals have been consumed, we are left with a few stable, large bodies, the planets, that have cleared their orbital paths.
Now, when we look at those resulting planets, there's an immediate, profound dichotomy that tells us the story of their formation conditions.
Absolutely. The solar system is neatly divided by the asteroid belt into 2 distinct families, which represent 2 different outcomes of that accretion process.
We have the inner planets, or terrestrial planets, Mercury, Venus, Earth, and Mars. What defines them?
They're defined by their proximity to the sun and their composition. They're small, dense, rocky worlds composed primarily of high melting point materials, silicates, rock, and metals like iron and nickel. Their density is incredibly high. Earth is 5.517 grams per cubic centimeter.
And then past the asteroid belt, a region where small bodies failed to accrete into a single planet, maybe because of Jupiter's overwhelming gravity, we find the outer planets, the Jovian planets, Jupiter, Saturn, Uranus, and Neptune.
These are a completely different animal. They're vastly larger, but counterintuitively, they are far less dense. They retain these huge, thick atmospheres composed mainly of hydrogen and helium, the 2 lightest elements.
Let's just revisit those density numbers because they are the shocking nugget here. Earth is 5.5 GC a meter, Jupiter is 1.333 GC a meters, and Saturn is the standout at just 0.723 GC a meter diameter. That means if you could find a bathtub large enough, Saturn would literally float.
That contrast, the fact that a planet thousands of times more massive than Earth could float, demands an explanation. And the sources point to two main interconnected conditions of formation that define the entire architecture of our system.
The first one is temperature, specifically the concept of the frost line.
Right, the frost line. It's the distance from the young sun where the temperature was low enough for highly volatile compounds like water, methane, and ammonia to condense into solid ice particles. Near the sun, inside this frost line, where the terrestrial planets formed, the temperature was so high that only the rocky and metallic compounds could solidify. Everything else was just vapor.
So the inner planets were built only from the comparatively scarce rock and metal available in the nebula.
Precisely. The outer planets, forming outside the frost line, had access not only for rock and metal, but also to vast quantities of water ice, methane ice, and ammonia ice. This massive increase in available raw material allowed them to grow enormous rocky cores, which then reached the critical mass necessary to gravitationally capture and hold on to the abundant hydrogen and helium gas.
And the second condition relates to the intensity of the early sun's output, the solar winds.
When the sun first ignited, it was emitting a far more violent outflow of energy and charged particles than it does today. Near the sun, this intense solar wind exerted significant pressure, effectively stripping away light gases and dust from the forming terrestrial planets. They simply couldn't hold on to their initial gaseous envelopes.
But the Jovian planets, being farther away, faced a much weaker solar wind.
They did. And that, coupled with the fact that they had already become so massive due to that abundance of icy material, meant their gravitational pull was enormous. They retained their thick, gaseous atmospheres, leading to the giant structures we see today. So it was the delicate balance between the material available temperature and the forces stripping it away, solar wind intensity, that determined whether a planet became a dense, small rock or a sprawling gas giant.
So we now have Earth, a dense, small, rocky planet formed approximately 4.6 billion years ago. But the violence of creation wasn't done yet. In fact, the next event was perhaps the single most important event defining Earth's subsequent history, the formation of the Moon.
The Moon's origin is unique, and it required a cataclysm. While earlier theories involved capture or co-formation, the current overwhelmingly supported model is the giant impact theory. It's often called the Big Splat.
And this wasn't a soft grazing. This was a head-on, planet-shattering collision that occurred very early, about 4.44 billion years ago, just 100 million years or so after Earth consolidated.
It required a body of immense size, a hypothetical protoplanet often named Theia, estimated to be between 1 and 3 times the size of Mars. This massive object struck the young Earth obliquely. The impact would have instantly vaporized huge portions of both the impactor and Earth's mantle, ejecting massive plumes of superheated molten debris into orbit.
Wait, a Mars-sized object hit us. What did that do to the planet besides just creating the Moon?
The effects were catastrophic and necessary. First, the collision instantly remelted most of the early Earth, resetting its geological clock and ensuring full differentiation, which we'll discuss in a moment. Second, the impact dramatically sped up Earth's rotation, giving us our relatively short day. And third, it gave Earth a significant axial tilt, which is fundamental to our seasons.
And the Moon itself formed from that superheated debris ring.
Yes. The material, which largely consisted of Earth's crust and mantle mixed with the impactor's material, coalesced in orbit over a relatively short period, maybe as little as a few thousand years, to form the Moon. The evidence for this is highly compelling. The Moon's density, for instance, it lacks a large iron core, suggesting it formed mostly from lighter crustal material. And moon rocks show isotopic compositions remarkably similar to Earth's mantle, but depleted in volatile elements, exactly what you would expect from a highly energetic, vaporizing impact.
The sources mention a compelling, if slightly speculative, detail that the immense depression caused by the separation of this material might be the massive basin now occupied by the Pacific Ocean. While we can't say that definitively today, it emphasizes the sheer magnitude of the material removed during this violent birth.
It certainly paints a picture of unparalleled devastation. After that huge impact, the Earth was a massive, hot, volatile sphere. This heat, however, was the engine for the next crucial stage: the evolution of the lithosphere, the sorting of the Earth's interior structure.
We've mentioned differentiation before, but let's delve into the mechanics. How did this mass of uniform hot rock decide to separate into distinct layers?
It was driven by continuous heating. The temperature inside the Earth was rising relentlessly. This internal heat came from two major sources. First, the kinetic energy from accretion, and the big splat, the lingering heat of formation. But second, and critically important for keeping the Earth active for billions of years, was the continuous process of radioactive decay.
This is the missing technical link we needed to focus on.
Absolutely. Within the early Earth were trace amounts of heavy, unstable isotopes, primarily uranium-238, thorium-232, and potassium-40. As these isotopes decay, they release heat energy. This steady, low-level internal heating, compounded by the initial impact energy, caused the entire planet to melt and become essentially fluid.
And once the material was molten, gravity took over in the process of differentiation.
It was a global density sorting event. Heavy materials, particularly liquid iron and nickel, were gravitationally unstable at the surface and began to sink rapidly toward the center. That's what formed the incredibly hot, dense inner and outer core. Simultaneously, the lighter silicon-rich compounds, silicate rocks, rose toward the surface.
Which means the Earth's layered structure, the iron core, the silicate mantle, and the thin outer crust, is a direct, inevitable result of physics and internal heat. A necessary step before anything resembling a continent could even form.
This stratification is the foundation of our entire planet's geology. It defines everything from the magnetic field, which is generated by the liquid outer core, to plate tectonics, which operates in the mantle. Without this early violent sorting event, Earth would likely still be a homogeneous, geologically inert sphere incapable of supporting complex life.
So now we have a layered, differentiated rocky sphere with a large moon. It's 4.4 billion years ago. But the surface is still a barren, rocky, hot landscape. And critically, it lacks the protective, life-sustaining atmosphere we enjoy today.
The next multi-billion-year process is about building the environment, going from a volatile, toxic state to the habitable Goldilocks zone. Our sources delineate three distinct, overlapping stages in the evolution of our atmosphere and hydrosphere.
Stage 1 is defined by what we lost, the loss of the primordial atmosphere.
When Earth first formed, it captured a thin blanket of the most abundant elements available in the solar nebula, hydrogen and helium. But as we discussed earlier in the context of terrestrial planet formation, these elements are incredibly light. Due to the high temperature of the young Earth and the continuous bombardment by the intense early solar winds, those light gases achieved escape velocity and were essentially stripped off, scattering into space. The Earth was left with a near vacuum.
So we had to build an atmosphere from scratch. Stage 2 introduced all the necessary ingredients via internal sources. This stage is degassing.
Degassing is the consequence of differentiation. As the interior continued to cool and solidify, the pressure built up. Volcanic eruptions, far more widespread and continuous than today, acted as vents, releasing immense quantities of trapped gases and water vapor from the interior.
And what were the ingredients of this second early atmosphere?
Water vapor was the most voluminous component, critical for forming the oceans. But the sources highlight the other major constituents: nitrogen, carbon dioxide, methane, and ammonia. And it's really important to note the composition of this early atmosphere. It was highly reducing and lacked any significant free oxygen. It was a toxic cocktail for anything resembling modern life.
And all that volcanic water vapor being constantly injected into the sky must have reached a tipping point.
It did, leading to the Great Rain. As the Earth's surface temperature slowly dropped below 100 degrees Celsius, that water vapor cooled, condensed, and began falling. This wasn't a week-long shower. This was likely continuous torrential rain over millions of years. This rain collected in the surface depressions and basins that had formed, creating the oceans around 4,000 million years ago.
The sources point out that this rain did something far more important than just filling basins. It began to alter the atmosphere's composition and temperature.
That's the climate stabilization mechanism. The enormous amount of carbon dioxide that had been released by the volcanoes dissolved into the rainwater. When CO2 dissolves, it forms carbonic acid. This acid then reacts with the exposed surface rocks, a process called silicate weathering, which pulls the carbon permanently out of the atmosphere and sequesters it into sedimentary rock.
That feedback loop is phenomenal. The rain pulls the CO2 out, which reduces the greenhouse effect, which allows the Earth to cool further, which allows more liquid water to remain stable, encouraging more rain.
It's the mechanism that prevented Earth from becoming a runaway greenhouse, like Venus. It was the formation of the hydrosphere, the oceans, that stabilized the temperature and provided the essential medium for stage 3, the ultimate biological engineering project.
Stage 3 is the modification by life, where life itself completely rewrote the planetary chemistry.
The oceans provided a shield and a stable chemical environment. The earliest life evolved around 3,800 million years ago, likely in deep-sea vents or protected shallow waters, starting with simple unicellular bacteria. But the true planet changer was the evolution of photosynthesis.
This process, starting with organisms like blue-green algae or cyanobacteria, began converting that abundant carbon dioxide into sugars, with oxygen as a waste product.
And this slow but relentless biological activity gradually began to flood the atmosphere with oxygen. It's a process known as the Great Oxidation Event, or GOE. Our sources date this shift to around 2,500 to 3,000 million years before the present. This was perhaps the first true planetary-scale pollution event.
Pollution. We think of oxygen as life-sustaining.
For modern life, yes. But for the dominant forms of life at that time, the anaerobic organisms that thrived in the methane and ammonia-rich atmosphere, oxygen was a deadly poison. The GOE was a huge extinction event for the old forms of life. It took hundreds of millions of years for the oxygen to reach a saturation point, around 2,000 million years ago, creating the oxygen-rich environment that allowed aerobic respiration and, eventually, the evolution of complex multicellular life.
Without those simple, ancient blue-green algae, Earth would still be a reddish, toxic wasteland. Our entire atmosphere is a biological artifact. Understanding the chemical evolution of Earth from volatile gas cloud to oxygenated world is essential because the origin of life is directly tied to those chemical changes. Life didn't appear randomly. It was a consequence of the early atmosphere being chemically conducive to forming complex organic molecules.
The conditions in that stage 2 atmosphere, rich in methane, ammonia, and water, were perfect for forming the complex building blocks of life. Energy from lightning, UV radiation, and hydrothermal vents likely drove this chemical assembly, leading to amino acids and nucleotide bases, which eventually organized themselves into self-duplicating entities. This process is called abiogenesis.
And when we look for the physical evidence of this event, the oldest geological record places the appearance of life incredibly early.
We find microscopic structures, often embedded in ancient rock formations, that are closely related to modern blue-green algae and other unicellular organisms. The consensus is that life began evolving sometime around 300–800 million years ago, very soon after the ocean stabilized and the Hadean Eon ended.
3.8 billion years is a number that immediately loses meaning because it's just so vast. To contextualize this deep dive properly, we have to use the geological timescale not just as a list, but as a scale for storytelling.
Let's use a powerful analogy to make that time frame comprehensible. Imagine the entire history of Earth, from its formation 4.6 billion years ago to the present day, compressed into a single 24-hour clock.
Okay, so 4.6 billion years equals 24 hours. Earth forms right at 12 a.m. midnight.
The Hadean Eon, from 4,800 to 300 million years ago, covers the first 5 to 6 hours, from midnight until about 5 a.m. This is the era of formation, differentiation, the big splat, and the origin of the oceans. It is a period of molten crust, constant bombardment, and intense volatility. No life could possibly exist.
Then, running from roughly 5 a.m. to around 1 p.m., we have the Archean. That's 3,800 to 2,500 million years ago.
This is the dawn of biology. The first unicellular bacteria and the early blue-green algae appear around 4 or 5 a.m. on our clock. For the next 8 hours, life is solely microscopic. These simple organisms spend this entire massive time period slowly working on the planet's atmosphere, initiating the Great Oxidation Event.
The next vast stretch is the Proterozoic Eon, from 2,500 to 570 million years ago. This runs from roughly 1 p.m. to almost 9 p.m. on our clock.
This is the age of transition. It's defined by the slow, painful process of oxygenation and the first inklings of multicellularity. We see the emergence of marine invertebrates and soft-bodied arthropods. Life is still primarily aquatic, but it's learning to use oxygen and to cooperate in larger structures.
Think of that. Nearly 21 hours of Earth's history have passed, and we still haven't seen anything resembling a plant or a fish. Finally, at roughly 9 p.m. on our 24-hour clock, we enter the Phanerozoic Eon, the age of visible life, running from 570 million years ago to the present.
This is the eon most familiar to people, and yet it represents only the last 15% of Earth's history. It's split into 3 major eras.
The Paleozoic era runs from about 9 p.m. to around 11 p.m. on our clock. This sees the first fish, the move of life onto land by amphibians, the appearance of early reptiles, and the formation of the vast coal beds during the Carboniferous period. Life just explodes into complexity once that initial hurdle of oxygenation is overcome.
Then comes the Mesozoic era, middle life, running from roughly 11 p.m. to 11.4 p.m. This is the iconic age of dinosaurs, peaking during the Jurassic. It's also where we see the appearance of the first flowering plants. This entire vast era ends with a catastrophic extinction event that wiped out the non-avian dinosaurs.
And that brings us to the Cenozoic era, from 65 million years ago to the present, which starts around 11.4 p.m. This is the age of mammals, as they diversify into the ecological niches left vacant by the dinosaurs.
If we look closely at the very end of that timescale, the Quaternary period, which runs from 2 million years ago to the present, is where we finally find human evolution.
Let's nail the final perspective point. Let's bring the clock analogy to its ultimate conclusion. If the Earth formed at midnight and the dinosaurs died off 20 minutes before the next midnight, when did modern humans, Homo sapiens, appear?
We appear in the Quaternary period, within the last 10,000 years. On our 24-hour geological clock, modern human history, the entirety of recorded civilization, agriculture, writing, and the internet, has taken place in the final 0.2 of a second before midnight.
That puts the immensity of the Hadean and Archean eons, those billions of years of just chemistry and rock formation, into such profound perspective. Our entire existence is an infinitesimal flicker at the very end of a 13.7 billion year cosmic story.
This deep dive has spanned 4 colossal dimensions: time, gravity, thermodynamics, and chemistry. We started with a singular point 13.7 billion years ago, moved through the forging of heavy elements in supernovae, condensed our solar system 4.6 billion years ago, and experienced the catastrophic Big Splat that gave us the moon.
We then watched the planet build its own atmosphere through degassing and fundamentally alter its own destiny through the Great Oxidation Event, driven by simple life forms in the oceans 3 billion years ago. Every stage was violent, requiring specific chaotic events, a supernova, a stellar collision, to create the necessary conditions for our existence.
The air we breathe, the layered structure of the crust we stand on, and the very water that sustains us are not givens. They are direct, hard-won products of these multi-billion-year processes. The key insight is not just what happened, but how precise the conditions needed to be.
What's truly provocative, then, is to look at the consequences of that early violence. Think back to the giant impact theory, the Big Splat. That event created the moon, which is the necessary evil that allowed life to thrive.
It did. The sheer mass of the moon, relative to Earth, stabilizes our axial tilt. Without the moon pulling us steady, Earth's tilt would wobble wildly over millions of years, causing extreme, devastating climate changes that would make complex life impossible to sustain for long periods. The moon also drives our tides, which were critical mixing engines for early chemical evolution in shallow seas.
So here's the final thought for you to mull over. The violence of the Big Splat, the catastrophic event that nearly destroyed the young Earth, was not merely an interesting footnote. It was the necessary precursor for the axial stability and climate regulation that made human life possible billions of years later. Our current stable home is a direct, indispensable legacy of that initial planetary collision. The thing that defines our stability began with the ultimate destruction,